Welcome back to Compiler Construction. In today's lecture, we'll take a closer look at optimizations. So this lecture consists of two parts. So first, we're going to define a data structure we can use to define and analyze optimizations, the control flow graphs. And in the second part of our lecture today, we'll take a closer look at liveness properties of variables. So for optimization, we want to apply a number of program transformations, and we apply these program transformations to improve the non-functional properties of a program, so for example runtime or energy consumption, without changing any of the meaning of our program. And we've already seen that we could apply these transformations either at the intermediate representation level, and there might be some of the transformations or optimizations we might want to apply at a lower level, so especially at the machine language level towards the end of our compiler tool flow. We have to ensure that these optimizations are safe. So safe optimizations means that the optimized program always has to give the same result as the unoptimized program, no matter which path through our program we take. So no matter which if conditions are taken, which loop iterations are taken, and how many loop iterations are taken, and which functions are called. And in order to do this in a structured way, we need some structured approaches so we can really ensure that our optimizations are safe. So let's take a closer look at the meaning of programs. The information that we need to perform optimization very often is not explicitly stated in the source code. What does this mean? Now, if it is not explicitly stated, it's somewhere implicitly stated, which means we have to reverse engineer this information, or just we have to extract this information from the code. And as an example, let's start with the following code sequence here. So we have 5 instructions, which are just all assignments here. And the first question we could ask ourselves when we want to apply an optimization is, are all of these statements actually necessary? Now, if we take a closer look, we'll find that some of the statements in our code are what we call dead code. So dead code means an instruction, if it's executed, it produces a value, like in these assignments here, it produces a value for x and for z, but this value is never used, so it's never read again before this variable is reassigned. And if we take a closer look, we see that the value of the variable x here in the first line is directly overwritten in line 3 without being read in line 2 or 3 in any intermediate step. And the same happens for the value of z, which we assign in this line here, so its value is never read because it's immediately overwritten in the line after. So if we know that our 2 lines marked in red here are actually dead code, we can leave them out. So this would result in a shorter program here, which is identical in terms of the output of our program, so the meaning of our program. So we would just take all the remaining lines of code, and we have a program that does exactly the same calculation. Now, control flow is linear in our example here, so the dead state of instruction is very obvious, but it becomes harder to do this analysis when control flow is involved in the execution of our program. So the first instance of control flow that can be involved are conditions, so if statements, if then else statements. So let's just add a bit of control flow to our example here. So in line 3, instead of executing this assignment unconditionally, we execute it only if a condition C is true. So now we have to reevaluate if all the other statements are still dead or if something happens to them. And if we take a look at this assignment of x here, we see that this assignment of x is only overwritten here if this condition C, which we know nothing about here, if this condition C is true. So if this condition C is false, it means, on the other hand, that this value of x here would actually be the one used in our last line of code here, which assigns the value of x to variable z. So this means that the first assignment to x is used in some cases, so in all cases where C is false, whereas in all cases where C is true, then the value of x that would be used on the last line here is the value inside of the then clause of our if statement. So the assignment becomes relevant when the value of C is false. Now things get even more complicated if we insert a loop, because we can run through the body of a loop multiple times, or we can enter the loop for the first time when entering through the while statement here. So if we insert a loop that covers the first 4 statements and the 5th statement, z equals x is the first statement after the loop, then we actually are unable to omit either statement. So we know that when we leave the loop here, so when this condition is no longer true, then we read a value of x here. And this value of x, as we've seen before, depends on the condition of C within the loop, within our last loop iteration to be precise. So if C was false in our last loop iteration before we jumped over to the end of our loop, then the first assignment here would be used. And if C was false in the final iteration of our loop, then this assignment here would be used as before. Now the other statement that was still dead in our previous example is the statement z equals 1. So we need to ask ourselves if this statement now is also still dead. Now in our previous example, z equals 1 was unconditionally in any case followed by z equals x. Now we can actually go through the loop again for after the assignment of z, which means that this value of z now could be reused in the assignment for y here, and also conditionally in the assignment for x here. So this value of z is no longer dead because in any case it propagates back to a following loop iteration here. So as you see, an analysis gets more complicated the more ways you have to actually execute passes through your program. Now the situation gets even worse when you switch from your source code view to our low-level intermediate representation code view, because we no longer have explicit notations of control flow using ifs or whiles, but we only have control flow changes through jumps, which can be either unconditional, so we jump in any case, or conditional jumps, which test a condition before they decide if they take the branch or if they don't take the branch, which means they just fall through and continue with the instruction that is after this conditional branch instruction. So control flow is not that obvious anymore, and in our example, when we translate it to intermediate representation, we have different control flows. For example, at the end of our loop body, we would jump back to the start of our loop, so we have a jump which is unconditional to label 1, which marks the start of our loop here, where we check our loop condition again. And this checking of a loop condition now decides if we enter the body of our loop here, or if our loop has finished, and then we jump beyond the end of our loop to label L2, which is the label of the first statement after the end of our loop body here. So the blue arrows here, the blue arcs, indicate the control flow, and we have additional control flow, of course, in this if statement. We omitted here. But we have also data dependencies, and these data dependencies are different to our control flow dependencies. So a data dependency can go backward in our loops, so it can go from our last iteration in our loop last instruction in our loop body here, z equals 1, to the next iteration through our loop body. So for example, to this assignment here, or to that one here. We didn't show all the possible dependencies here. And we can have a dependency of a value from inside of the loop body to an instruction that's executed after the end of our loop. So in order to properly do optimizations on IR level, which is of course what we want, we would need a number of methods to compute information. And these methods should be implicit in the program. They should be static, so we should be able to execute them at compile time by just looking at the program's code or intermediate representation without trying to execute this code. So that would be dynamic. And it should be valid, or all of the methods we are going to use should be valid for every possible dynamic situation. So they should be valid no matter which path through our program we take, so no matter which if or else statements we take, how many iterations through a loop we take, or which functions we would call conditionally, which would only be determined at runtime. So using our static analysis, we would have to cover all the cases, all the possible ways that execution can take through our program. So in addition to these methods, we need a data structure to base our analysis on. And this data structure should be able to represent every possible control flow. So it should be able to represent all the different branches taken, so conditional branches, And it should also be able to represent the branches taken a different number of times, so iterations of a loop body. And the problem is very similar to the problem we had seen with NFAs before, so we need to find out what are all the possible passes I can actually take when I'm currently analyzing my program at a given point in my program. And this data structure we are going to base our analysis upon is called a control flow graph, or short CFG. So what we're trying to do is we try to capture the program's control flow in a directed graph, and the parts of these directed graph now represent parts of our program. So statements are represented as nodes in our control flow graph, and the sequences of statements are represented by the arcs in our control flow graph. So if we want to consider the movement of data, because the control flow graph, as the name says, captures the control flow, so capturing the movement of data can be inferred if we traverse this graph from start to end, for example. And this is by far the most common approach that is taken in present compilers. Note that you can also turn this on its head, so you could also construct a data flow graph and infer the control flow from this. This is not that common, so for our compiler lecture here, we'll stick to the control flow view of our program. Now, in our control flow graph, multiple paths of execution through our program can emerge, since some of the nodes will have multiple incoming and outgoing arcs, so at runtime a decision is taken which of the arcs to take, and we need to consider all of these possibilities at static analysis at compile time. So let's try to construct the parts of our control flow graph, and let's start with the very simple part here, linear code sequences. Now, a linear code sequence looks like this. So we have just a number of assignments, for example, without executing any control flow, so without any loops or if statements here. So what we can do is, of course, we know that there's implicit control flow, so we know implicitly after our computer has executed the first assignment here, it will execute the second assignment, and after the second assignment, it will continue to execute our third assignment here. Now, note that this is still taking the view of a computer as a von Neumann machine, even though, of course, your real computer nowadays might be superscalar, so your real machine might decide to actually optimize the code execution by executing the first two assignments in parallel and then executing the third assignment here afterwards. Now, even the superscalar machines takes care of providing this illusion of being a von Neumann machine on the machine language level, which is what we're going to ultimately generate. So essentially, we don't have to care about details like these. Now, there are architectures which actually expose internals of the architecture, so we have to take care of this when generating machine code. So one example for this might be the MIPS architecture, where there's something called branch delay slots, or the Itanium architecture, where there's a VLRW architecture, where we have to explicitly state which of the machine instructions we generate can be executed at the same time, so in parallel, which means there are no data dependencies between them. But on our intermediate representation level here, we don't take care of that. We just assume that the machine is such a simple von Neumann executing machine, which just sequences instructions unless it has to execute control flow. Now, our control flow graph for our three instructions then looks like this. So we have our first assignment A equals 1, then we automatically fall through. So our control flow continues at the second assignment, B equals 2. And finally, we arrive at our last instruction here, C equals A plus B. Now, of course, if we would have a control flow graph at that level of detail here, it would get very complex. So what we do is we contract all of our single assignments again into a basic block, and we've seen basic blocks before. But we have to remember that there are separate statements inside of the basic block, so it means that even though we have contracted all of those to a single basic block, one of the statements or more of these statements inside of our basic block may become dead code nevertheless. So For branches, again, it gets a bit more complicated, and we've already seen that a branch ends a basic block. So whenever there's a branch, we have a change in control flow. So we need to execute code either the one way or the other way. So if we take a look at our example code here on the left-hand side, we see that we have an if statement here with a then and an else part, and then execution continues after the if statement with our part doing the final assignment to Z here. So this part of code, this piece of code needs multiple basic blocks here, and we know that a basic block ends whenever there's a control flow change that is possible. So the first control flow change that's possible is after the if statement. So because the if statement then, depending on the condition, either takes a control flow through our then part here, if C was true, or it takes our the control flow through our else part here whenever C up here is false. Afterwards, both control flows convene again in the instruction after the end of our if then else statement here. So which basic blocks is this code made of now? Now we have two assignments here first, so that's an automatic fall through. We've already seen this on the previous slide. And we also have an automatic fall through to our if statement because we're not jumping to the start of our if statement anywhere. So our first 3 lines of code here make up our first basic block, and then we have to end the basic block because we know that there's a branch involved. So this is our first basic block here. So our second basic block is what is inside of our then block here. So we again have two assignments here, which come one after the other, so they can form one basic block. And then we don't have an explicit jump statement, but what we have is an implicit jump, because whenever we reach the end of our then block, we automatically continue not in the else block here, but we continue with the first instruction after our else block. So with that instruction here, so at the end of our then block is an implicit jump to the first line after the end of our if then else statement. So this again ends our basic block, so we end up with our second basic block here. Now the same is the case for our else block here, because we jump into it, we start a new basic block here. And now we could say, of course, we fall through automatically to this instruction after the end of the else, but since we could also jump implicitly from the end of our then block to that instruction here, we need an additional basic block for our final instruction here. And so our control flow graph looks like this. We have our first basic block until the jump decision has to be taken, depending on our condition C, and then we either jump to the left basic block in our then clause, or the right basic block here if the condition was false, and then our control flows converge again after the end of the then or else block, and continue with this final line of code that we have shown on the left hand side. So what we can do now is we can assign just unique numbers to each basic block. So we have B1, B2, and so on. That makes it easier to just denote control flows to through our program. And we now see that every possible execution of our program is actually encoded in the control flow graph. So no matter what the condition C is, either we take the left control flow here and end up at the last instruction, or we take the one on the right hand side and end at the same instruction again. And there is no other control flow that can be executed here. So all control flows here, every possible way of execution of this program is encoded here, and each of the passes corresponds to a run of the program. So in this case corresponds to the current value of C that was just active at this point in time when we actually executed the program. And C could maybe be a variable you just read from the keyboard to be true or false. So you could not actually predict what the value of C was when you statically analyze the program, because you can't really predict the input. So we know that when C is true, we would always take the left path through our control flow, and whenever C is false, we'll take the right path through our control flow, but our combined control flow graphs always encodes both possibilities in the same graph. Now, an interesting question is if there are any infeasible paths through our control flow graph. So some of the passes may actually not correspond to any possible run. So let's assume we extend our control flow graph a bit. So we have an if statement here that decides based on a condition C if it should execute then or else. Then our control flow converges. And then we have another if statement checking the same condition C and again deciding if to take the then or the else part before continuing with the rest of our program. Now note that we assume for our analysis here that neither the then or the else part here changes our variable C. So this actually creates the possibility to have some infeasible executions encoded in our control flow graph. So for example, the path we show here, going first to the left-hand side to the then statement as a result of executing a jump after the first if, and then going to the right-hand side for the second if statement to the else statement is actually impossible because the value of C hasn't changed. So if this value of C is, for example, true, we would always take the left part, which is not shown here, for the second if statement, and if the value of C is false, we would always take the right side part here, but there is no way through our program that could actually execute a pass like this, because this would imply that the value of C had changed between our first and second if statement, which is something we explicitly excluded in our assumptions here. So this means that without pruning the infeasible passes, so looking at certain combinations that can actually never occur, and as we've seen this might require runtime information, our analysis will remain conservative, so it might cover more cases in its static analysis than would actually occur in real-life execution of our program. So it's conservative, or we also call it safe, as long as every actual pass that can happen through the execution of our program is actually also represented. So this means if we have an outgoing arc from one basic block to another in our control flow graph, that the destination of an outgoing arc may be a successor to a basic block, but it does not always have to be, because in some cases it would be an infeasible path. And on the other hand, it means that an incoming arc may be a predecessor, so the source of that arc, so the other side of that arc, may be a predecessor to a basic block, but it does not have to be in all of the cases we consider here. So what we want to do is to construct our control flow graph, and as you can imagine, we do it in a recursive way, like so many other things in compilers. And at a high level, our control flow graph can be constructed using a syntax-directed scheme. And this works very similar to our construction of 3-address code by translating it into lower and lower representations here. So if we have a simple statement of sequences S1 to Sn, we know that our control flow for the simple statement of sequences looks like this. We first have S1, and then we automatically fall through to S2, to S3, and so on until we arrive at statement Sn. And if we want to construct the control flow graph of an if statement here, so if expression, then execute S1, else execute something called S2 here, then we have a control flow graph that actually branches after the if to the left-hand side to S1 and on the right-hand side to S2. And we need to converge our control passes afterwards. And to do this, we insert an empty basic block here that helps us converging our control passes. And this recursive construction works similar for simple if statement here that don't have an else part. So if expression execute S looks like this. So either we jump to the left-hand side and execute our basic block for S, or a statement or sequence of basic blocks, whatever is inside of S. And on the other hand, if this condition is not true, we just fall through to our empty basic block here at the end where our control flow converges again. And for while loops, it also looks similar. So if we have a while loop, while expression, execute our loop body S, then we have two passes to enter our loop. So first we can enter it to a regular control flow when we encounter while for the first time, or we can go through our loop once, so we would enter it again after executing our loop body. And there's also two ways to leave the if statement here. So either you can go inside of the loop whenever your condition is true, or you can leave the loop whenever this expression is false. And in order to enable the easy construction of a recursively built control flow graph, we add an empty basic block after the end of our while loop again. So let us now try to apply our construction approach recursively. So what we do is we take our program as a whole, and then we split it into the syntactic parts which we can recognize, and then we recursively go through all of these parts here to obtain more and more detail of our control flow graph until we have arrived at single statements. So let's take a look at that complete program here. So we have a while loop here with the loop body, and we have a single statement after the end of our while loop here. So on a high level view, we have a sequence S1, which consists of the whole while loop here, and S2, which is just our assignment statement. So our high level control flow graph is we first execute the while loop, however many times, and then we execute our second statement here. So this is just a linear code sequence because we haven't looked inside of our while loop so far. So when we look inside of our while loop, now we have to add the recursive construction of our loop here. So now we can dig deeper into our while loop and we can recursively construct the control flow graph representing our while loop as we've seen before. So what we do is we split our while loop here into the parts actually checking the condition, which makes our first basic block here. So we have if C. So if the condition is no longer true, we add this empty basic block here at the end of our loop and then fall through to S2, which we generated in the step before. And if our condition C is true, we just add something that represents the body of our loop, and we know at the end of our loop body we jump back to the beginning of our loop to actually then check the condition again. So now we can split this up even further. So now we look at our loop body here, and we see our loop body here consists of a sequence of statement again. So we have one assignment, two assignments, then we have this if statement here, which we consider as one statement for the moment, and then our final assignment here. So inside of our loop body is just the sequence of these four blocks here. And then, of course, we have to dig deeper again because not all of these blocks were just single statements, so we're not yet finished. So finally, we'll have to take a look at this line with the if here. So this line is with the if, we know also has to be recursively then constructed into its own partial control flow graph. So it looks like that on the right hand side here. So it's an if without an else clause. So we either jump to the left hand side, which gives us this instruction here, or we jump over the then part and then our control flow passes converge after the end of our if. So essentially now we dug down to all the details which are part of our simple example program here. Now as you can see, even for this very simple program here, taking all the parts together, our control flow graph has already grown quite complex. So the next step we should do is try to prune this control flow graph to combine as many single statements into larger basic blocks as possible. I will do this on the next slide here. So we've seen that we can prune basic blocks or single statements together to form basic blocks here. So we can, for example, combine the first two assignments inside of our loop body here and the if statement here checking for the condition D to one single basic block here. And then we can just kick out all the empty basic blocks we've inserted and just add arcs to the basic blocks following our empty basic blocks. So we would end up with a control flow graph like this. So our loop is represented by the if statement, checking our condition C at the beginning, and then taking one of the possible passes through our loop body here. And we have two passes here, depending on our second condition D here. So either we take a detour through our then statement, or we directly fall through to the final assignment at the end of our loop body. And finally, if our loop condition C no longer holds, then we just exit the loop and jump to the first statement after the end of the loop. So As these graphs grow large, we need to ensure that we should have as few basic blocks as possible, and the basic blocks themselves should be as large as possible. And so what we do here is we merge the linear subgraphs if all these conditions hold. So if block B2 is a successor of block B1, and block B1 has only one outgoing edge, as well as block B2 only has one incoming edge. So we have a direct control flow that always automatically falls through from B1 to B2, and then we actually can combine these two blocks B1 and B2 into a single larger basic blocks, and we can continue this recursively until we find no more options to merge, and we can remove the empty blocks by just kicking them out and moving the arcs pointing to them to the arcs they are pointing to. Now we can also do this at a low-level intermediate representation. So this would mean we would split the operation sequence at labels and jumps, because these are the destinations and the sources of control flow changes. So labels have incoming control flow and jumps can have outgoing control flow. So for our example here, this would mean, well, we started our first basic block, and then the first instruction here already has a conditional jump, so this ends our first basic block here. We would jump to L2 down here. So our next basic block begins afterwards, and this ends at our next conditional statement here, which would jump to L3. So since L3 is a jump target here, our instruction x equals y plus z here is its own basic block. And then the next basic block starts at L3. This has a conditional jump back to L1, so this ends our fourth basic block here. And finally L2 we have seen as a branch target from up at the start of whatever was a loop before. So L2 and the instruction following it make up their own basic block again. So we've seen that a conditional jump always has two successors in a control flow graph. So either we take a jump or we don't take it, which means we fall through. But this falling through means we fall through to a different basic block. And this again means that we cannot combine them. So all of our conditional jumps here, like that one here, have two outgoing arcs here and the other one here. Whereas our unconditional jump L1 always only has one target here, which is up here to L1, so we only have one successor. And of course, we said initially that the meaning of the program must not be changed, and so it's no big surprise that the outcome of doing this analysis from a syntactical analysis, constructing the control flow graph, or from an IR representation, constructing the control flow graph again, is the same. So both procedures give us an output which represents the equivalent program logic. But of course, since we want to do our optimizations on IR level, the one on the right hand side here is the one that's of more use to us, whereas the one on the left hand side here is easier to understand if we come from a way to understand our source code program. Since we now know that without a proof both representations are equivalent, we can work with both as required in the remainder of this course.